Good afternoon. Good to see everybody here. A lot of old faces, new faces. It's great to see you guys. Over a lifetime of working in this industry, I've come across a lot of people, and all of them good, and it's just been a wonderful trip. And I'd like to share anything that I have with you for any reason that you need it. That's part of this. That's what this is about, is sharing it. Information isn't proprietary. It doesn't belong to any one person more than another person. It's just a matter of getting that information. And we'd like to pass that on as much as we can and help you go on with it. What we start with here is some pretty basic stuff. We don't get really in depth. I'm not going to try to troubleshoot a FireEye controller today on a class like this because we need to appeal to the entire audience as we do this. So as it goes on, if there's a question that you can ask that pertains to this particular thing, please feel free to ask it as we go. And at the end of the session, probably 5 or 10 minutes before we finish up, we'll open it up for just general questions, anything we can do. After class, I'm available for as long as you need or whatever. And anytime you need to, call, and if I can help you out, I'll be more than happy to. That's what we're here for. So we'll go on with this thing and see if I can make this work. I'm not a very technical guy, so let's see if I can make this. Well, let's go back. I'm getting too ahead of myself here. Okay, now let's go. Hang on, there we go. There we go. You should have this in front of you, and basically what it talks about, when we, people that do this for a living, I mean we being you and us together, I often explain it, we're nothing more or less than heat merchants. We move heat from one place to another. That's all we do. We either take heat out of something or put heat into something. And it applies to this first rule of thermodynamics. You can change the energy from one form to another. We take fuel and we change it into heat. Heat goes into the water. Water goes into the system. Heats the air, blah, blah, blah. So in the end, what happens is there's just a continuous cycle of this heat. The second law there states that it always flows from a higher temperature to a lower temperature. In other words, if you touch something and it feels warm to your touch, then you are cooler than the object you're touching. That same rule applies across the board in everything we do. Heat is always going to be transferred to the cooler of two objects. That's the way it works. So having that in mind, we're going to go through a couple of things. I don't want to stand in front of you guys here so you can see. We have boilers here, and there are a number of different varieties of boilers. I see a lot of people from a lot of different areas that have everything from a cast iron boiler to a large water tube boiler. There are many different styles and types, but they all, in essence, do the same thing. What they do is they have a box down in the bottom, in this particular case, and it burns fuel. That fuel produces heat. That heat transfers up, through, and around, and these are tubes that run through here. In this particular case, we've got water around the tubes. So this would be a fire tube boiler where the flame goes down through, passes back through, and passes back through again. And all of the water that's surrounding this jacket is then heated. The heat's transferred from the cooler, right? Nope. From the hotter to the cooler. It's always transferred from the flame and the heat of the material. So what we're doing is we're actually heating up. As we go through here, the flame produces the heat, but then the heat itself transfers. Flame only goes so far in a boiler, and the rest of it is just heat that's produced. So that heat then travels through these tubes, and it warms the surface of the tube. Usually it's metal. In some cases, and in the case of like domestic water, they use boilers for that. In domestic water boilers, it's oftentimes copper. Copper has a very quick heat transfer surface. So if you put heat into it, it transfers to the medium, the water, relatively quickly. There are always inherent problems with any design. Whether it's a fire tube, water tube, copper tube, it doesn't matter. There are certain things about each boiler that make it unique to itself and its application. Three main types that we see here are the cast iron. Now, oftentimes guys will call these sectional boilers. I know some of the smaller buildings, particularly buildings that don't have a big demand or that are older buildings, that it's very difficult to get in a larger boiler in there, will have cast iron boilers. Cast iron boilers are designed for a various range of BTUs, they have certain inherent characteristics. One of the things about cast iron is that it's like a radiator. Think of it as just big radiators that are put together. The radiator surface absorbs the heat, and cast iron, because it's porous, retains the heat for quite a while. It'll hold on to the heat and dissipate it slowly out into the water. So it's not something that's you're going to use a cast iron boiler for a high recovery process. If you were doing production work and you needed hot water or steam immediately, you would not use a cast iron. Cast iron is typically used for comfort heating in a building, is what it's typically used for. It's not typically used for process type work. The next style there is a fire tube. It's the one that's most commonly used in medium to large size buildings. The fire tube comes in a variety of sizes and shapes. The fire tube boiler comes, it can be coming in different styles, shapes, manufacturers. Each one, again, peculiar to itself, but each one doing the same thing. Typically, a fire tube boiler has got a power burner on the front of it. Skip back here just a second to the cast iron. This cast iron shows a power burner on the front of it, meaning what we have with a power burner is we have a large fan. And that fan blows the air and more or less supercharges the air in there and mixes the fuel and air together. Oftentimes, cast iron in smaller mediums has just what's called an atmospheric burner. It'd be similar to what you'd have in your furnace. It just has a ribbon strip of heat underneath it, and it just heats that area. A little less effective. It's not very effective when it comes to adjustment. There's very little you can do. You can set the gas pressure and make sure that the air shutters are correct, but other than that, there's not a lot you can do. So the power burner on any model is always a step up. So we put the power burner on a cast iron and we get more efficiency and we get it quicker. On the fire tube, it requires, in this day and age, a power burner. Years ago, it didn't. There were old systems that used to just have a big fire box, and they used to feed it with coal or fuel oil or anything else they wanted to feed it with, and it got extremely hot. And through natural radiation convection, the flame and heat would rise and come through here. Very slow to process. Because of the cost of fuel nowadays, we want to get away from that kind of stuff. We want this thing to be as efficient as we can be. And that's part of our job, is to help you keep these things efficient. The more efficient it is, the less cost it is, the longer it lasts, everybody wins. The water tube boiler. The water tube boiler typically is seen in a couple of ways. Because the water is actually in the tubes, the water actually goes in the tubes and the flame is around the tubes. Most of these have a 1.5 to 2 inch diameter tube. Can be larger, can be smaller, but just as an example. What happens in a large water tube boiler is the heat is around the surface area much quicker. So that if you're building steam, for example, a water tube boiler is excellent for producing large volumes of steam very quickly. It doesn't have a lot of reserve steam because it produces it so quickly and so much in volume. In the water tube boiler, there's a couple of terms you might hear. Across the top up here, this is called the steam drum. Along the bottom, on either side or one side, depending again on the configuration, it's called the mud drum. What happens is the water level would be normally about halfway up this. As it boils, it has to have somewhere to go. So the water boils and comes to the steam drum. Proportional to the size of the boiler, the steam drum is not very large. It's merely a place for the steam to come from each individual tube to arrive at and then be transported through piping to wherever it's going. I don't know how many guys have worked on them. I don't know how many know about them. Power plants. If you go to a power plant, Iatan, for example, over here in the bottoms, most of the coal-burning fire plants that we have around here are nothing more than a water tube boiler. What you're looking at when you see that massive structure standing out there, 6, 7, 8 stories, sometimes more, is nothing more than a boiler. That is the boiler. The stack that you see is nothing more than the flue. All the other crap around it is just crap around it. And that's what we're paying for, is the crap around it. We're paying for the electricity. But from our standpoint, that whole building is nothing but one humongous boiler. That's what it does, and it's a water tube boiler, almost exclusively. I've never seen one that isn't. The reason being, large volumes of steam, high pressure steam, relatively quickly and continuously. Once these things start burning, they produce a tremendous amount of heat very, very, very rapidly. There are a few of the hospitals, in fact most of the hospitals here in Kansas City, use this style of water tube boiler. They're relatively large. Small ones would be as tall as this room, large ones would be as big as this building. So there are just a number of places that use that. But for the most part, what I want to deal with are these two down here, because these are relatively obscure and they're very particular in their nature. Scotch Marine boiler is a fire tube boiler that has a flue furnace and a horizontal shell. This particular one is a Cleaver Brooks. It doesn't matter about the manufacturer. What they call this a fire tube is because there's one main tube going down through here. And then from that tube, it hits the back wall and turns and comes up through the other tubes a number of passes. An easy way to know how many passes you've got, and therefore somewhat idea of how the efficiency is, if it goes down through here and comes back up, if the stack, the flue stack is in the front, it's an even number. It'll either be 2 or 4. Rarely do you find one that's 6. That's very uncommon. So it's either 2 or 4 passes. If the stack is in the back, it's going to be an odd number. It'll probably be 3, more than likely. You could have as many as 5, but not likely. 4 passes in a boiler are about what you normally see for a high efficiency boiler. Reason being, we have to produce this heat. And as this heat goes through here and gives up its value, which is we measure in temperature, as the temperature, the value reduces, as remember the heat that's being produced from the flame reduces, then a couple of things happen. First of all, of course, is we're going to produce hot water or steam. The second thing that happens is the flame itself becomes what's called quenched. It's cooled down. The flame is cooled down, and the gas that's going up, the heat that's going up the stack, is cooled down. That's good because we want to wring every available BTU of heat that we can out of that heat source. However, there is a break point in everything. And once you get to the certain break point, if the flue temperature is not maintained at a minimum, then what happens is byproducts are produced in the flue gas. And as the byproducts are produced in the flue gas, that's where the problem arises. So you don't like to run a boiler in cold temperatures. The exception to that would be the most modern of what they call the condensing boilers. These high efficiency condensing boilers are made to operate at that very low temperature rate. But that's the exception again, it's not the rule. And so I'm not going to deal with that, that's a whole different subject altogether. What you want to do is maintain a flue temperature that keeps the gases in the stack a minimum, so that this minimum so it won't drop below that minimum temperature. And really where it boils down to is that again goes back to 1 or 2 other items. The minimum flue temperature is based on a couple of things. 1, how many passes? 1 pass, 2 passes, 3 passes, 4. The more passes, the cooler the gas that's going up. The more heat is being wrung out. If you have a water tube boiler, for example, the very minimum temperature you want to run in a water tube boiler is 160 degrees. Now that's an arguable number. That number could be 158.4, I'm not exactly sure. It would vary on the conditions. But just as a rule of thumb, if you maintain 160 degrees hot water leaving your boiler, you are going to help ensure that these byproducts of combustion, these gases, this acid, this water that's going to form, does not form in there. If it's below 160, you're going to be guaranteed that it's going to form. Small portions of it, livable. Large portions of it, damaging. 2 ways. Eats up the metal inside, creates what's called NOx, going out the stack, NOx. It's nitric oxide, and it's what the government's going to be looking for in the future. It's their biggest thing, that's their biggest kick that they've been on for some time, and it hasn't arrived here in this part of the country, but it's a lot of other places. So, Scotch Marine. Oftentimes we wonder the question, Scotch Marine, why Scotch Marine? Well, I'm not sure, it could be just a little bit derogatory in some cases actually, because what you have here, the Scotch Marine, the marine boiler was built to go on board ships. They made a regular fire tube boiler, but they compacted its size and made it more compact and smaller to fit in the low headrooms of ships.